Hello everybody, my name is Konrad Wiśniewski and I'm working with a group of experimental physicists on a capacitance measurement of polycrystalline solar cells. At some point of my PhD, I decided to create a program based on finite element methods to simulate transients in polycrystalline solar cells. And right now I want to show you why these kind of simulations are important and to show you some of my results. When I'm talking about the capacitance, what I actually mean is dynamic capacitance, which is very easy to understand on an example of p-n junction. To measure the capacitance, you just need to add some external voltage to the sample and look how many carriers go in or go out of the device. In some cases, there exist point defects in the structure which can influence our measurement. For example, they can capture or emit a hole. If we will investigate our experimental signal, we can gain a lot of information about what's going on inside of the device. I use Deep Level Transient Spectroscopy, and the idea behind this experiment is very simple. You just applied some voltage, and here you look what happens with the capacitance. Just to show you some of the problem that we had in experiment, in a standard DLTS theory, we should see the curve similar to that on this plot. But in experiment, the sign of the signal is twisted. And moreover, when we get rid of the voltage, we can also see the signal, which is much more bigger, and we even shouldn't see it at all. So the idea is that we shouldn't look at the point defects in the structure, but on the spatial defects, I mean the grain boundaries, or maybe some barriers between back contact and absorber. In my program, I used classical van Roosebeek model, and I used mixed finite element methods to solve the Poisson equation, the G method to solve drift diffusion equations, and I used explicit time stepping to update time in my simulations. And if someone wants to have some details, my work was based on the article shown here below. I used deal.ii library and UMF pack to solve my equations, and my code is uploaded on my GitHub, so you can look at it there. I'll look into three scenarios: the p-n junction with Schottky contact on the left, or the horizontal grain boundary, or vertical grain boundary. So I was able to calculate the structure with additional Schottky junction, unfortunately with small but still negative charge densities. And after that, I tried to look how the capacitance of this whole structure will change with time when I will apply external voltage. This is how this capacitance transients can look like. And the most interesting part is that all of the part on the right hand side is the consequence only of the way I calculate the capacitance. It's not connected to any physical phenomenon, so this can be the reason why we can see these very strange experimental signals. I simulate grain boundary by the big density of the traps in this region. And from capacitance measurement, we can calculate the doping profiles, and this is what we see. And this is what we see right now. And as you can see, when I add more traps on the grain boundary, the profile starts to strongly deviate what we can expect. But it starts to look very similar to what we can see in experiment. I have also some problem during my simulation. For example, the time step. Some part of the dynamics in this structure lasts for nanoseconds, and another one can last for 1 second. So I need to have a good way to transfer from one side step to another. If someone know how to do it properly, please share this knowledge with me. Maybe in a comment it will be very helpful. And also I have some issues with the convergence in vertical grain boundaries, and it is probably because I start from not very physical initial conditions. So this is a summary, and thank you very much for your attention, and enjoy the rest of the conference.